Sorry, you can start. Sorry, that's not trouble.
Are we all set?
Yeah, you can start. Sorry.
Okay. Let's see where we left off last time. We were looking at some details of the circuit analysis of a two-port network connected up to a Thevenin equivalent source with an internal impedance at Z1 and a source voltage E1. We decided to make use of a matched source so that Z1 was actually equal to Z0. And connected up at the other end of the two-port is a matched load, in general Z2, but for a matched load Z2 would also be set equal to Z0. And we were doing some circuit analysis on that circuit to come up with some interesting results. The first result that we ended up with was an interpretation of the incident and reflected waves as being related to the power incident and reflected off of the two ports. And remember, the subscript here, I, is just 1 or 2, depending on whether we're talking about port 1 or port 2. Precisely, the relationship is that if you take the magnitude of the wave squared, multiply by the factor of 1/2 to take into account average power, then the average power incident on port 1 or 2 is given by that quantity. The reflected power off of the port being given by this quantity in terms of the reflected wave. Let's see, what else did we find out? We found out that the incident power, or that is to say the power incident on the port where the source is connected, can also be written in terms of the magnitude of the voltage supplied by the voltage source, that's that E1, in the following way, as magnitude of E1 squared divided by 8Z0. Now this is for the case where the internal impedance, the Thevenin impedance of the source, is E0, is equal to the characteristic impedance of the transmission line connecting the source up to the two-port. That's the maximum possible power that the source can supply. If the internal impedance of the source was not 50 ohms, was not Z0, then it would supply less power to the two-port, and you'd end up with a value for P1 plus that was smaller than this. So this is actually the greatest possible value that P1 plus can take on. And notice that it's equal to magnitude of E1 squared divided by 8Z0. This is a very common factor, E1 squared divided by 8Z0. We give it a name, call it the power available from the source, and it's equal to this quantity for a matched source. Remember, the factor of 8 comes from the fact that we have the 1/2 due to time average power, just like you always have 1/2 of VI conjugate and so on when you're dealing with average power in terms of peak phasors. But we get this extra factor of 2 because of the fact that the source has an internal impedance of Z0, the line has an impedance of Z0, so the power that actually makes it onto the line, you have to use the voltage from the source divided, a voltage division factor of Z0 over Z0 plus Z0, or 1/2. So that accounts for the extra factor of 1/2, which when squared becomes a 1/4, so overall we have 1/8. The power available from the source is equal to this quantity for a matched source. We then looked at the reflected power back up the line toward the generator, reflected off of the two-port when you've got a source supplying, let's say, PAVS. That is to say, we looked at 1/2 of B1 squared and found out that it could be written in terms of the power supplied by the source minus the total power, and ended up with well, the quantity we had at the bottom of the previous page. Then we looked at the power delivered to the load, given by 1/2 of magnitude of B2 squared, and found that it could be written in this form. Okay, now what I'm going to do next is to give you a simple method by which we can calculate the scattering parameters for simple circuits. Let's say we have a simple circuit making up the two-port in question. Then we can do actual circuit computations. Just pencil and paper computations using basic circuit theory to predict what the scattering parameters are going to be. This is a good way to calculate scattering parameters when you've got simple circuits that are enclosed inside of that square box that is the two-port. This simple method of calculating scattering parameters that I'm going to show you is not so useful for a lot of realistic two-ports, where the circuit analysis that I'm going to talk about here becomes a little bit messy. But let's assume that we've got a relatively simple circuit inside of our two-port. Then one way to characterize the scattering parameter S11 is in the following way. It can be written as ZT1 minus Z0 over ZT1 plus Z0, where this ZT1 thing is something that we're used to dealing with in circuit theory. ZT1 is the impedance looking into port 1 of the two-port device when port 2 is match terminated. So if the two-port consists of a simple circuit, let's say a couple of resistors connected in series and parallel and so on, then put one more resistor on that circuit. Put a resistor of Z0 on port 2 and calculate the input impedance. Call that input impedance, looking into port 1, when you have that extra resistor of Z0 on port 2, call it ZT1. Then do this simple calculation in terms of that input impedance, and you get the numerical value of S11. I'll do an example of such a calculation in just a moment. It can also be shown, and I'll ask you to take a look at the textbook for the demonstration of this fact, that the magnitude of S11 squared can also be found in terms of power quantities. The power available from the source minus the total power at port 1 divided by the power available from the source. This equation for the magnitude of S11 magnitude squared is not as often used in this particular form. A form that this equation is most often used in is multiplying both sides by PAVS and solving for P1. What you end up with is P1, the power at port 1, is the power available from the source times a quantity 1 minus S11 squared. That means that the total power incident at port 1 is the power available from the source minus this multiple of the power available from the source, magnitude S11 squared times the power available from the source. And thinking back to the equation that said that the power was equal to the available power, the incident power minus the reflected power, that tells us that PAVS must be the incident power, and PAVS times magnitude S11 squared, that's the reflected power at port 1. The amount of that incident power that doesn't make it into the two-port network, but instead is reflected right off of port 1 back toward the source. We can come up with formulas for calculation of S21 as well by making use of this definition of S21 as the power out of port 2 divided by, the wave out of port 2 divided by the wave into port 1 when we have a matched termination on port 2 to make A2 equal to 0. This is just the definition of S21. But I had formulas previously for these two quantities. Here they are. And nicely enough, the square root of Z0 cancels out, and I have the following formula in terms of the circuit quantities. Current emerging from port 2 and current incident on port 1. That can be used along with the original circuit that we were looking at. Here's the original circuit, Thevenin equivalent source connected up to port 1, matched load connected up to port 2, and doing a little bit of circuit analysis to figure out what that ratio here is equal to. Here's the result. You can show that, once again I'll refer you to the book for the intermediate steps. You can show that S21 can be written in the following form. S21 is equal to twice the voltage at port 2 divided by the voltage of the Thevenin equivalent source E1. Refer to this circuit up here. Okay, what that's saying is I could calculate S21 with a paper and pencil calculation on a circuit if the two-port was some sort of a simple circuit by doing the following things. Connect up a Thevenin equivalent source with magnitude of E1 and Thevenin equivalent impedance E0. Connect up a load of Z0 up to port 2 and find the voltage V2. Use circuit analysis to calculate V2, the voltage at port 2. That voltage at port 2, of course, will depend on what the voltage E1 of the source is. Well, to find S11, take that voltage out of port 2, multiply it by 2, and divide by E1. That will eliminate the dependence on the source voltage, and you'll end up with a pure number. Complex number, but a pure number for S21. I'll do that as an example as well. In terms of powers in the text, the following equality is shown. That is that the magnitude of S21 squared is equal to the power at the load divided by the power available from the source. That is to say, magnitude of S21 squared is the ratio of power delivered to the load divided by power available from the source. This is another important quantity. We're going to see it a lot, so we'll give it a name. We'll call it the transducer power gain of the two-port network. So here's our definition of the transducer power gain. Magnitude S21 squared. PL over PAVS, which in terms of those voltages from the source and the voltage at the load can be also written in the following way. All right. Now, those two equations that I just derived for S11 and S22 are important. You might want to even put a box around this equation for S11. I'll do an example of calculating S11 using that equation. Similarly, of all these equations that we've been going through in the past couple of pages, this is an important equation for S21. Put a box around that one too. I'll do an example calculating that one. How about the other two scattering parameters? There are two more, S22 and S12. I am not going to go through any analysis at all to find formulas for those two. I am simply going to wave my hands and invoke this magical word of duality and say that by duality, since I already have formulas for S11 and S21, I automatically already have formulas for S22 and S12. And the way I get the appropriate formulas for S22 and S12 from the other formulas is take those other formulas and everywhere you see a 1, replace it by a 2. Wherever you see a 2, replace it by a 1. This is a concept known as duality. Basically, it's a completely rigorous argument that says that just because I labeled one port port 1 and the other one port 2, that was just an arbitrary convention. I could just as easily have called the other port port 1 and the first port port 2 and done the exact same circuit analysis in reverse. And I would have got the exact same results by analyzing that so-called dual circuit. All right, so I could go through all the circuit analysis again, but it would bore you to death because I do the same analysis over again, except instead of starting from the left and working toward the right, I'd be starting from the right and working toward the left with the exact same circuits. All right, so I'm going to invoke duality to say that to come up with a formula for S22, well, just take that old formula for S11 and put a 2 where you saw a 1 before and write it as ZT2 minus Z0 over ZT2 plus Z0. So there's the important formula for S22, where ZT2, well, ZT1 was the impedance looking into port 1 when port 2 was matched. I guess ZT2 would be the impedance looking into port 2 when port 1 is matched, right? Just replace 2's by 1's everywhere, even in the description. And, of course, S22, we've already seen, is interpreted as the output reflection coefficient when the input is matched. Do a similar circuit analysis that we did when we were talking about S21 to show that S12 is twice the voltage at port 1 when port 2 has a Thevenin equivalent source with voltage E2 connected to it. So this is the formula for S12 that we use in circuit analysis for computing S12. The circuit that you use in order to compute S12 is the dual circuit that we used when we were talking about S21. Remember when we were talking about S21, we put a matched source on port 1 and a matched load on port 2. Now I guess we'd be putting a matched source on port 2 and a matched load on port 1, replacing 1's by 2's and 2's by 1's to be able to use this idea of duality. And the magnitude of S12 squared is also given a name. It's not quite as important. I'm not even going to give it a symbol this time. It's called the reverse transducer power gain of the two-port. And it has a formula in terms of the voltage at port 1 and the source voltage of the source connected up to port 2, as shown here. Okay. Now, let's take a look at an example of the use of these formulas for the scattering parameters of a simple circuit. Here's a very simple circuit. Couldn't get much simpler than this. It's just an L connection of a 50 ohm resistor and a 100 ohm resistor. I'm going to assume that we're talking about a 50 ohm system. That means characteristic impedance is 50 ohms in the calculations I'm going to be doing here. And I'm going to use my formulas and circuit theory, to calculate the scattering parameters of this very simple circuit. Okay. Now, in order to make use of the formulas for the scattering parameters, I'm going to do things like place a matched Thevenin equivalent source over here onto port 1 and a matched load over here onto port 2, and calculate things like the input impedance looking into port 1 and the voltage across port 2 given that voltage source connected up to port 1, and so on and so forth. Or maybe I should say, and vice versa. Using duality, I'm going to also be connecting up a source to port 2 and a load to port 1 and doing those calculations too. Before I enter into those calculations, though, I'm going to normalize this circuit. I'm going to divide the impedances and all impedances that I make use of in my calculations by 50 ohms before proceeding. This is a convenient thing to be able to do, and it turns out it will have no effect on the answers that I get for the scattering parameters, a fact that I'll be demonstrating in just a few more minutes. So for calculating the two scattering parameters S11 and S21, that's where I place a matched source on port 1 and a matched load on port 2. That is to say, a voltage source of 50 ohms impedance to port 1 and a 50 ohm load up to port 2. So this is the circuit I make use of for calculating the two scattering parameters S11 and S21. Here's the matched source connected up to the L-shaped two-port circuit, and here's the matched load. I've divided the impedance. If we could come back to the slides here. There we go. I've divided all impedances by 50 ohms, the characteristic impedance or the system impedance, just to simplify my calculations. So the 100 ohm resistance here becomes 2 once I normalize it. The 50 ohm resistance here becomes 1. Here's a 50 ohm Thevenin equivalent source connected up to port 1 and a 50 ohm load connected up to port 2. All right, now to calculate S11, I need to first calculate the input impedance looking into the two-port when I have a matched load on port 2. I'm looking for the input impedance looking into the terminals of the two-port when I have a matched load. That is to say, back up here in the original circuit, imagine putting a 50 ohm resistor here on port 2 and asking the question, what's the impedance looking into port 1? That's ZT1 that we're talking about in our equation for S11. Okay, well that's something I could hand to a student in Networks 1 class. And that student would say, well, the input impedance looking into these terminals is equal to a series combination of this 1 ohm resistor in series with a parallel combination of a 2 ohm and a 1 ohm resistor. This is the way I write that result. It's the input impedance is 1 plus, for the series connection, 2 in parallel with 1. 2 in parallel with 1. That's my notation. That is to say 1 plus 2 in parallel with 1. What's the impedance of a 2 ohm resistor in parallel with a 1 ohm resistor? It's 2 times 1 over 2 plus 1, right? Z1, Z2 over Z1 plus Z2, 2/3, in other words. So 1 plus 2/3, 5/3. That's the impedance looking into these terminals, input terminals of the 2-port, when it has a matched load connected to the output terminals. Then the formula for S11 in terms of that input impedance is ZT1 minus Z0 over ZT1 plus Z0. That was the original equation. But remember, I have everything divided by 50 ohms, divided by Z0. So that formula for normalized circuit, like I have here, is ZT minus 1 over ZT plus 1. 50 divided by 50 being equal to 1. I just found ZT1, 5/3. So it's 5/3 minus 1 over 5/3 plus 1. That just gives me 1/4 as a result. Right 1 is 3 over 3. Then you have 5/3 minus 3/3 over 5/3 plus 3/3. The thirds cancel out. And we end up with 2 divided by 8, or 1/4. How about S21? Well, this same circuit will do it for me. S21, the boxed formula that we had from the notes, S21 was twice V2 divided by ES. So, do a circuit analysis, calculate V2 in this circuit. Assume that you're given ES, and find V2 in terms of ES. Then, take twice V2 that you find and divide by ES, and that is it. That's S21. Okay, well, let's find V2 first. Well, let's see. V2, I can use voltage division to find V2 in terms of ES. Because the voltage ES is divided between a voltage across these 2 resistors. Part of ES falls across these 2 resistors, and the remainder of V2 falls across the parallel combination of the 2 ohm and 1 ohm resistor. That's the part I want. How much voltage is there across that parallel combination? So, use the voltage divider rule. The voltage divider rule says the voltage in question is equal to the total voltage times the impedance of the portion of the circuit that we're trying to find the voltage drop across, divided by the total impedance. So, V2 is the total voltage ES times the voltage division factor of the impedance of the portion of the circuit that we're trying to find the voltage across, which is 2 ohms in parallel with 1 ohm, 2 ohms in parallel with 1 ohm, divided by the entire impedance, which is this impedance plus that impedance. It's 1 plus 1 plus the 2 in parallel with 1. 1 plus 1 plus 2 in parallel with 1. Okay, we've already found 2 in parallel with 1. That's 2/3. Then 2 plus 2/3 is 8/3. So the voltage division factor gives us V2 being equal to ES divided by 4. Okay, well now we're just about done because S21 is twice V2 divided by ES. So take this quantity, multiply it by 2, and divide it by ES. Nicely enough, the ES's cancel, and we just end up with 1/4 times 2, or 1/2, as the final result. So we've now found the scattering parameter S21 for this circuit. All right, now let's do the dual calculations to find the other two scattering parameters. Take this circuit, and instead of placing a matched source on port 1 and a matched load on port 2, let's do it the other way around. Let's put the matched source on port 2 and the matched load on port 1. So the circuit we're going to be dealing with for the other two scattering parameters looks like this. There's the original circuit, the 50 ohm and 100 ohm resistors in their L configuration. Now I connect matched source up to port 2, 1 for its internal impedance and E sub S for its magnitude, and a matched load up to port 1, 50 ohm resistor, or 1, since we're dealing with normalized impedances. And now here's the voltage V1 that we're going to need to calculate to find S12, and here's the input impedance looking into port 2 when port 1 is matched. It's this input impedance looking into these terminals of the original 2-port, now with a 50 ohm load or matched load. Okay, well, what's that input impedance? Now the input impedance is equal to the 2 ohm resistance in parallel with 1 plus 1. That is to say, 2 ohm in parallel with 2 ohm, 2 in parallel with 2. That's the way I write it here. 2 times 2 over 2 plus 2, 1. So there's ZT2. Here's the formula from the notes for S22. If you know ZT2, all you have to do is this simple calculation. ZT2 minus 50 over ZT2 plus ZT2 minus Z0 over ZT2 plus Z0, but we're normalizing everything, dividing everything by Z0. So it's just ZT2 minus 1 over ZT2 plus 1. When ZT2 is 1, big fat 0. S22 for the original 2-port. Here, S22 is equal to 0. How about the last scattering parameter, S12? That's the one where we need to calculate the voltage that would appear across the matched load in terms of the source voltage ES. Then we take twice V1 and divide it by ES in order to find S12. Okay, so let's concentrate on finding V1 in this circuit. All right, this circuit's a little bit more complicated than the circuit we had up above. Let me approach finding V1 in 2 steps. Let me first find the voltage V at this point, the voltage at this node, or the voltage across the 2 ohm resistor, or the voltage across the 1 plus 1 here. First find V1, V, and then find V1 in terms of V. Okay, V. Well, I can use a voltage divider for the source voltage in order to find V. because the source voltage is divided. Part of ES is dropped across the 1 ohm resistor, and the rest of ES is dropped across this slightly more complicated circuit here, which consists of a 2 ohm resistor in parallel with the series combination of a 1 ohm and a 1 ohm. That is to say, the total resistance of that portion of the network is 2 in parallel with 2. Well, we've already done that one. 2 in parallel with 2 is just 1. Okay, so ES, V. We want ES as, V is going to be ES times the voltage division factor of the impedance of the portion of the circuit that we're trying to find the voltage drop across. V is the voltage drop across the 2 ohm resistor in parallel with the 1 plus 1. That's what we want. So ES times that impedance of that portion of the network divided by the total impedance, the impedance of this portion of the network and this impedance of 1. So the voltage V is ES times 2 in parallel with 2 divided by 1 plus 2 in parallel with 2. 1 plus 2 in parallel with 2. Well, 2 in parallel with 2 is 1, so it's 1 over 1 plus 1 ES times 1/2, or ES divided by 2. That's the voltage V. Okay, but that's not what we wanted, actually. We wanted the voltage V1, but we can find V1 easily enough in terms of V, because the voltage V is the voltage drop across both of these resistors, both of these two 1 ohm resistors, and we want the voltage drop across this 1 ohm resistor. What is that in terms of V? V1 is just going to be half of V, right? Half of V will be dropped across this 1 ohm resistor. The other half of V would be dropped across that 1 ohm resistor. Or more rigorously, we could use voltage division to find V1 in terms of V, because the voltage V would be divided between these two 1 ohm resistors, and the voltage division factor would be 1 over 1 plus 1, the total resistance. So V1 is V times 1 over 1 plus 1, or once again, 1/2 of V. V times 1 over 1 plus 1, or V over 2. But we found V in terms of ES. So plug in this first equality for V to get V1 is equal to ES divided by 4. That's the result that we needed. Because S21, by definition, twice V1 over ES, it's twice this quantity divided by ES. 1/2 is the numerical result. So we've now found the other two scattering parameters, S22 and S12. Remember, we already found S11 and S21, so we know all 4 scattering parameters of the original circuit in a 50 ohm system. Note that S11 has a value of 1/4 and S22 has a value of 0. But S21 forward transducer gain is 1/4. S12, the backward transducer gain, was also equal to 1/4. Turns out you can show that this is actually always the case, that for any passive circuit, S12 and S21 are going to be equal to each other. You can't say anything similar for the reflection coefficients S11 and S22, though. Okay, so there's the example. You've got a problem that looks very similar to this on the homework assignment due next time. A little more complicated. That one's a pi-shaped network rather than just an L-shaped network. It has 3 resistors rather than 2. But you're being asked to do the exact same thing. You're being asked to put a matched source onto port 1 and a matched load onto port 2 and do some circuit calculations to find these 2 scattering parameters, and then do another circuit calculation where you put the matched source onto port 2 and the matched load onto port 1 and do some circuit calculations to find the other 2 scattering parameters. Any questions on this example? Okay. Turning back to the notes then, we're almost done with chapter 1 now. Section 1.7 of the textbook we're not going to worry about. Section 1.8 talks about converting from one set of network parameters to another. Basically, that table, which is called figure 181, plus the table that I provided in the textbook, are the main formulas of interest there. One other set of interesting relationships is the relationship between the impedance parameters and the scattering parameters, which can be written in terms of matrix equations, it turns out. And here are the appropriate matrix equations. The scattering matrix can be written in the following form in terms of the characteristic impedance Z0, that's just a 50 scalar number, Z0, and the impedance matrix Z11, Z12, Z21, Z22, and the identity matrix, and this other combination of the Z matrix and the identity matrix. Z plus Z0 times I inverse over Z minus Z0 times I. These 2 matrices in parentheses multiplied by one another, where you have to remember this is a matrix inverse, the inverse of the matrix in parentheses here. Similarly, there's a simple relationship for the reverse direction. Given the scattering matrix S, you can perform the following operation with the scattering matrix. 1 plus the I, the identity matrix, 1, 0, 0, 1, the 2 by 2 identity matrix plus S times the identity matrix minus S inverse, multiply those matrices together, multiply the result by 50, and you'll have the Z matrix. These matrix equations are in ideal form for numerical computation. Computers love to work with matrix equations of this form. It's also interesting to make the comparison of these matrix equations relating the scattering matrix and the impedance matrix to the analogous equations which relate reflection coefficient gamma with a load impedance Z. on a transmission line of characteristic impedance Z0. It turns out that these two equations, for the scattering matrix and for the impedance matrix, are the matrix analogs of the corresponding equations relating reflection coefficient and load impedance in the transmission line problem. To see that, write the equations for the transmission line problem. Here are the equations I'm talking about. We found that the reflection coefficient is equal to ZL minus Z0 over ZL plus Z0, where I'm just calling ZL plain old Z here. Let's just drop the subscript L and remember that we're talking about the load impedance there. You can solve that first equation for Z in terms of Z0 and gamma. And this is an equation that we will be using quite a bit later on in this course. Z is equal to Z0 times 1 plus gamma over 1 minus gamma. That's just the inverse of the first equation. Just the first equation solved for Z in terms of gamma. Compare with the equations up above. They're basically an identical form. Z minus Z0 over Z plus Z0. Z minus Z0 divided by Z plus Z0. Or Z minus Z0 times Z plus Z0 inverse. Z minus Z0 times Z plus Z0 inverse. Same equation, only in matrix form. And of course, you can't just take a matrix and add or subtract Z0. You've got to make Z0 into a matrix. And the simplest way to make Z0 into a matrix is just multiply the identity matrix times that factor of Z0. So that equation and that equation are analogous to each other. And so are the second pair of equations. Z in terms of gamma. Only now S plays the role of gamma. S is the scattering matrix. So we have Z0 times 1 plus gamma divided by 1 minus gamma, or Z0 times 1 plus gamma times 1 minus gamma inverse. Z0 times 1 plus gamma times 1 minus gamma inverse. Where 1, well, we've got to talk about identity matrix instead. And gamma is now the scattering matrix. Okay, just an interesting analogy that allows me to remember the pair of equations in matrix form relating those parameters. Okay, we're not going to discuss in any detail the measurement of the scattering parameters in the laboratory. Suffice it to say there's a piece of equipment to use in the laboratory called a network analyzer that allows you to very easily measure all of the scattering parameters of any two-port device. And in the microwaves and RF lab 4553, the network analyzer is one of the central pieces of equipment being used. In this class, we're going to assume that the measurement has been done for us. For the transistors, for instance, that we're going to be making use of in our high-frequency amplifiers, the manufacturer supplies, along with those transistors, the corresponding data sheets that give the values of the scattering parameters. The scattering parameters are either tabulated, given in a table, or sometimes also they're even graphed as a function of several different things. If you take a transistor and bias it in different ways, you'll get different behavior for the transistor. And it should come as no surprise that biasing an RF transistor at different bias points will give rise to different scattering parameters. So the manufacturer will typically give the values of the scattering parameters of the device for several different typical biasing conditions for the device. And the biasing condition that you make use of may not be exactly the same as one of the ones that the manufacturer supplies scattering parameters for, in which case you might have to interpolate between different values for biasing conditions that are near to the biasing condition that you make use of. But another thing that causes variation in the actual values of the scattering parameters is the frequency of operation of the transistor. And this should also come as no surprise, that the scattering parameters vary as a function of frequency. Because after all, we know already that for normal low-frequency transistors, the gain, let's say, of the transistor is often very strongly frequency dependent. And you can get a very good strong value of gain at lower frequencies, but once you start pushing the frequency up into the amplifier up into higher and higher frequencies, the value of the gain generally will decrease as frequency is increased. And in general, the H parameters or Z parameters or any other low parameter set, low frequency parameter set for the transistor, those parameters are also functions of frequency. Well, the scattering parameters are as well. And here's a typical, somewhat idealized graph of the variation of the values of different scattering parameters, or at least their magnitudes here, as a function of frequency. I'm choosing a logarithmic frequency scale and also a logarithmic scale for the values of the magnitudes of the scattering parameters. And what you find is that at low frequencies, the forward transducer gain has nice large values, let's say, for a typical transistor. But as you increase in frequency, you get decrease in the value of the transducer gain. The frequency F beta, where the value of the forward gain starts decreasing, is often called the beta cutoff frequency. And that forward transducer gain gets lower and lower and lower as frequency is increased until finally the gain becomes unity gain, or on my logarithmic scale, the logarithmic gain becomes 0. That value of frequency, where the transducer power gain of the device passes through 0, is called the transducer cutoff frequency, F sub s. And at values of frequency even higher than the cutoff frequency, the transistor no longer acts as an amplifier. It actually attenuates the signals passing through. S12, the reverse gain, is typically very small, but it increases as frequency increases, usually leveling off somewhere around the transducer cutoff frequency. And S12 and S21 can be multiplied together to show that their product behaves in some sort of a fashion as shown here. Straight line between the beta cutoff frequency and the transducer cutoff frequency, increasing below and decreasing above. Now, the reason why we're not going to worry about having to measure the values of the scattering parameters at different frequencies in this course is because we're going to make use of the ADS software and simulation of the circuits. And the ADS software has an extensive library of commonly used RF transistors. And the scattering parameters that are cataloged in this library are scattering parameters that are measured for a large range of frequencies. So you specify your frequency of operation, and the ADS software will pluck out of that database the appropriate values of the scattering parameters at that particular frequency. Okay. There are equivalent circuit models for BJTs and FETs that are used in all sorts of more complicated circuit analysis of circuits that contain RF, BJTs, and FETs. We're not going to go into them in any detail in this course. You can take a look at section 11 of the textbook if you're interested. This material is material that's covered in more detail in the follow-on course, RF devices and circuits. Okay, and that does it for chapter 1. Now we're ready to move on to chapter 2, which deals with the Smith chart. So, it's time now to have ready Smith charts and compass. Here's my compass and some sort of a straight edge in order to draw some straight lines. What we're going to do here is primarily just a review of the pertinent information on Smith charts. I'm not going to be introducing anything that is completely new here in my material on Smith charts, except for a couple minor points that I will slow down and cover in a little bit more detail as I move through this material. But for purposes of most of the material in this chapter, I consider it review material that you've seen already in your course on fields and waves. And it's gone over in quite some detail in the textbook. I'm once again following the organization of the textbook here. And also, any good fields and waves text can be used as a reference on this material. Okay. Why the Smith chart? Well, as we've seen already, the impedance and voltage and current and so on a transmission line vary in a somewhat complicated manner as you move up and down the transmission line. For instance, something of interest to us is the impedance. at any particular point on a transmission line. And in particular, the input impedance of a section of transmission line. When you set x equal to minus L in this formula, that's what we call Zn. I'm going to use the fact that Z is a complex quantity and write it as a complex quantity in rectangular form as shown here as R of x plus j times x of x. Z is a function of x, a function of position, so its real portion, the resistance at any portion on the line, is a function of position, and its reactance, the imaginary part of the impedance, is also a function of position on the line. And as usual, there's our definition of what we mean by the impedance at any point, phasor voltage divided by phasor current, and there's the actual formula that we derived in the last chapter for the impedance as a function of position, where we remember that quantity beta x, or beta L, is equal to what we call the electrical length. Beta is 2 pi over lambda, so we can write it as 2 pi x divided by lambda, sort of a normalized version of the position on the line, the value of x with respect to a wavelength. The Smith chart is a very useful way of avoiding a lot of very tedious calculations with formulas like this. And not only that, but it provides us with some real insight as to how transmission lines and their loads interact with one another. You might think that now in this age of computers and computer-aided design, which we're going to take full advantage of in this course, that the Smith chart as a graphical method, most graphical methods sort of go out the window once computers are introduced, because computers could care less how complicated an equation like that looks. The computer will crunch on that equation as easily as it will any other. However, let's say that you're trying to design a circuit that involves transmission lines operating at RF. And you want to get a feel for how you would change different things in that design to get that design to work the way that you want it to work. Well, you could have the computer go through all the different various cases for you, compute the value of the input impedance for all possible lengths of the line, and for all possible values of the load impedance, for all possible frequencies. And you'd come up with a long, long list, page after page after page, of complex numbers, different input impedances for different lengths, different frequencies, different loads, and so on and so forth. And you want your circuit to behave in a certain way. Looking at that page after page worth of complex numbers isn't going to tell you a whole lot unless you do something like graph those numbers and see how they vary as a function of frequency or as a function of load impedance and so on, and get some feel as to how the line length affects the input impedance, and a feel as to how frequency changes things, so that you can get an idea and say, aha, it looks like if I just increase the frequency up to about such and such a value but no further, that should be a good value. And then you'll try that one in your design. You don't get that out of just looking at the numbers. You get that out of the graphics. And the Smith chart is one such a graphic. As a matter of fact, in using these CAD programs for design of RF circuits, rather than printing out page after page worth of complex numbers, what the output of the computer program, like ADS, usually consists of is a graph. And that graph for most RF circuits is a Smith chart. And so the ADS software will print a Smith chart for you and draw a curve on that Smith chart. And then you can see that Smith chart on the display and take your pointer and point to one location on the curve, and it'll show the value of the impedance at that point. You just move the cursor around to another point, click on that one, you see the impedance at that point, and so on. So the standard output for most computer-aided design software at RF is the Smith chart. It's a very important thing that is not going to be going away anytime soon. Even computers make use of the Smith chart. All right, well, the Smith chart, what is it? Well, any passive load that you can talk about, where by passive we mean a load which has a real part which is positive, real part of Z sub L greater than or equal to 0 is what we define as a passive load. For any passive load, the impedance on the line up here, given by this formula, the impedance of any point on the line, as long as Z sub L is a passive load, is located somewhere in the right half impedance plane. That means that the impedance Z that you end up with, it's kind of a complicated function of Z sub L and location on the line and so on, but one thing is guaranteed. If Z sub L has a real part greater than 0, then Z is going to have a real part greater than 0 also. That is to say, this R value is going to also be greater than 0. But that's about all that you can say easily. Now, what happens if you change the value of Z sub L? Where in the right half impedance plane is Z going to be located? What happens if you change location on the line, X? Where is Z going to be located? What happens if you change the frequency? Where is the impedance Z going to be located? Not easy to say, other than that for a passive load, the location of Z is going to be somewhere in the right half plane. That's where the Smith chart comes in. Let me start by making a simple little drawing that I find useful, and I hope you might as well. Let's see if I can wake this thing up. Doesn't look like the power is on. There we go. I got some green lights blinking. That must mean I'm moving in the right direction anyway. Let's focus. I want wide. Yeah, something like this. Okay. Okay, I'm going to try to illustrate something that I call the, I keep messing with focus, I don't want to do that. Something that I'm going to call the evolution of the Smith chart. Hello, come back. There we go. From the right half impedance plane. Okay, so let's say that this is the right half impedance plane. Where any impedance with a positive real part, that is, any impedance that I'm calling a passive impedance, is located somewhere on this right half plane. Now you could draw that right half plane on a graph. And you might have your lines of constant resistance and lines of constant reactance making up the grid on your piece of graph paper. I'm going to subject this right half impedance plane to the following mathematical transformation. Gamma equals z minus 1 over z plus 1. Why am I going to do this? Well, the reflection coefficient on a transmission line was defined as zl minus z0 over zl plus z0. I'm going to normalize that equation first. I'm going to divide it by z0. So it becomes z, small z, minus 1 over small z plus 1, where small z is equal to z divided by z0. And the 1, well, that's just z0 minus, over z0. Okay, that's the mathematical transformation that transforms the right half impedance plane into the Smith chart. I'm going to do this in a way that mathematicians would object to. What I'm going to do is I'm going to do this transformation in steps. I'm going to imagine that it's possible to sort of morph this right half impedance plane into a Smith chart using that equation. And I'm going to freeze that transformation about halfway through and show you what it would look like partway through the transformation from a rectangular right half impedance plane into the plane that's defined by this variable gamma, z minus 1 divided by z plus 1. Okay, here's what happens, is that the resistance axis, the r-axis, starts shrinking. It starts shrinking in, actually in a sort of a nonlinear fashion. I'll show you what I mean by a nonlinear fashion in just a second. The x-axis both shrinks and curves as it shrinks. Starts looking something like this. And what happens to the grid? what happens to the graph paper, the lines on the graph paper, as this transformation is performed? Well, here's what happens to those nice lines of constant resistance. They start curving too. And because of the fact that the r-axis is shrinking, they start getting closer and closer to one another. Something like that. And the lines of constant x, they also become curved. They still intersect the blue lines at right angles, but in order to do that, they've got to start curving. And so they will start looking something like this. They curve and start getting closer together themselves. Okay. Well, let's bring this transformation to an end. Let's go the rest of the way through the transformation. Okay, here's how things end up. The r-axis shrinks so far in that the original resistance axis for the right half plane that went from 0 to infinity shrinks down to unit length. It becomes of unit length. And the x-axis becomes so curved that the entire x-axis curves in like that. And at x equals plus infinity, it actually touches the r-axis at infinity, which is shrunk down to unit length. And what we're left with is a real bad drawing of a Smith chart. Very much distorted here. Sorry about that. My artistic abilities are not the greatest. Here's what happened to those lines of constant resistance. They've shrunk down until they're also completely enclosed, becoming circles. They don't look like circles the way I have them drawn here. Believe me, on the Smith chart they actually are. And those lines of constant reactance, they now become arcs of circles. They still intersect the blue curves at right angles. May not look like it on my drawing, but check out a Smith chart and you can convince yourself of that fact. They end up looking like that. And that, as I say, is my real bad rendition of the Smith chart. So this is the way I remember what the various curves on the Smith chart are supposed to represent. I remember this picture of the right half impedance plane curving in on itself and morphing to become the interior of what we call the Smith chart. And I remember that the lines of constant resistance, I can see that those would become those curves. the blue curves, and the lines of constant reactance in the normal impedance plane become these arcs inside of the Smith chart. So that's a picture that I use to help me understand the Smith chart. Okay, well, let's turn back to the notes and take a look at the mathematics and forget about my lousy artistic ability. What I'm going to do is, first thing I'm going to do is, as promised, define the normalized impedance. It's easiest to work with normalized variables, and we do that a lot in RF. Normalized variables, be they impedance or voltage or anything else, we usually denote by small letters corresponding to the unnormalized variables with capital letters. So normalized impedance, small z, is the actual impedance, capital Z, divided by the characteristic impedance, Z0, or divided by 50 ohms. Well, Z was R plus JX, capital R plus J capital X, so that is what we divide by Z0. And we call the real part of the normalized impedance small r, just like the real part of capital Z was capital R, and the imaginary part of the normalized impedance is small x. Now, here's the equation that gave us the reflection coefficient in terms of the impedance. We found that gamma was Z minus Z0 over Z plus Z0. Or, in terms of normalized impedance, take the numerator and denominator here and divide both numerator and denominator by Z0. We get small z here, and we get 1s, plus 1 and minus 1, there and there. And that's the reflection coefficient gamma. The reflection coefficient is itself a complex number, because z is in general a complex impedance. And we call the real part of the reflection coefficient u, the imaginary part we call v. This is this relationship between z and gamma, or between r plus jx and u plus jv. That's a well-known transformation for mathematicians. Mathematicians call that a complex bilinear transformation. And one property that a mathematician can prove is that any complex bilinear transformation always maps straight lines and circles in one plane into straight lines and circles in the other plane. That is to say, if you had a straight line or a circle in the z-plane, you're going to get either a straight line or a circle in the gamma plane. You have to understand that straight lines can be mapped into circles and circles can be mapped into straight lines, so we can in general say that lines and circles get mapped into lines and circles by any transformation of this sort. Also, these types of transformations preserve angles. What that means is that if you have two lines that cross at a given angle in one plane, the curves corresponding to those lines in the other plane will cross at the exact same angle. And so, given the grid of the graph paper in the right half impedance plane, since those lines crossed at right angles, that's why I say the circles corresponding to those lines in the Smith chart always cross one another at right angles. A transformation that maps the complex right half plane in the z-plane into the unit circle in the gamma plane, that's the Smith chart. That's what I just got done drawing there. And there they are. There's the right half impedance plane. And there's the Smith chart, complete with the U and V axes being drawn in here. This drawing didn't end up so awful great. That should be a 1 here, and that should be a 1 here, indicating that this is the unit circle in the gamma plane. So the Smith chart can be thought of as the unit circle in the complex gamma plane. And any point in this complex gamma plane has a U coordinate and it has a V coordinate, U being the real part of gamma and V being the imaginary part of gamma. That's when you write gamma in rectangular form. However, we're going to usually be writing gamma in polar form. So given a point in the Smith chart, usually we draw a line connecting the origin to that point and measure the length of that line, and we measure the angle that that line makes with the plus U axis, and refer to gamma in polar form rather than in rectangular form. Okay, so there it is. There's the Smith chart. These are posted on Blackboard. Download a bunch of them. And also you'll find posted on Blackboard the other version of the Smith chart that's called the YZ Smith chart. Download some of those too. This is a slightly more complicated version of the normal Smith chart. It's really 2 Smith charts in one. And we'll be going through this one as well next time. Okay, also, remember we have an assignment due next time in class, and I will have solutions posted soon thereafter. Also, I've got a computer assignment that I'm going to be assigning maybe next time. If not next time, then a week from today. So stay tuned. You'll be seeing your first computer assignment using the ADS software appearing on Blackboard soon as well. Okay, we're about out of time. Make sure you bring your compass, straight edge, and Smith charts with you next time so that you can follow my examples that I give in lecture. Any questions before we call it a day? All right. See you all Thursday.